So let us continue the study of some topological aspects of the Hopf's umlaut, which will ultimately go into the Gauss-Bonnet theorem. So last time we studied the lifting property of a function which is defined into the circle. The direct consequence of that one today very easily is the following. Start with a convex subset of Rn. Take any smooth function from X to the unit circle S1. Start with any point x0 in X and choose some real number E in R0 such that E of R0 is f of x0, which just means that this is cos 2 pi R0, comma sin 2 pi R0. That is my notation for E. Under these hypotheses, there exists a unique map G from X to R such that E composite G is F. So this F can be lifted to a unique map G. Moreover, if F is, say, of class CR, then G is CR. If F is smooth, then G is smooth. If you just say F is continuous, then you can say only G is continuous. So this is the conclusion of this theorem. The proof is obtained very easily when you understand what is the meaning of a convex subset of Rn. I hope everybody understands convex subset of Rn. If any 2 points are there in X, say P and Q, then the line segment joining P and Q should be completely contained inside X. So that is the meaning of that X is convex, right? So having that property allows us to define a function capital H from X cross 0, 1 to S1 by this formula. It is f of something. What is that something? It is, you have fixed one point x0, remember that. So look at the line segment x0 to x. So it can be parameterized 1 minus t times x0 to plus t times x. When t is 0, this is x0. When t is 1, it is x. So it's the line segment. On the line segment, the entire line segment is contained inside x. So f is defined. So I take f of that. So h of xt is f of that. Obviously, if f is continuous, if capital H is continuous, if f is smooth function, it will be smooth function of whatever order you have. The important property of this is, just now I told you, if t is 0, okay, if t is 0, then this tf goes away, this is just x0. This is f of x0. So for all x, it is f of x0, which means that this is a constant function. H of x0, h of x on the entire x is constant function. When x equal to 1, when t equal to 1, h of x1, when t equal to 1 here, it is just fx. So it is a given function. Okay. So what we have is the function f is homotopic to the constant function f x0. Okay. Via this homotopy, provided x is a convex set. So this is all the topology here. But once you have a homotopy, one map can be lifted by some function g, then the whole homotopy can be lifted. So that was the theorem that we proved last time. So therefore, by taking g equal to just R0, g of x equal to R0 is a constant function, that is the lift of fx0, right, h of x0. So I have a g here. This will guarantee me capital G from x cross 0, 1 to R such that E composite G is H, and the initial segment, that is G of x0, is just G of x, which is R naught for all x, a single point. Okay. Now you look at the other end. Okay, G of, we may call it as H or something. There is a G you have to want it, so you have to distinguish between G. This G is taken in the other theorem. Here I take G equal to Gx1, the end point. That is the lift of fx, because G of E of this is nothing but E of G, which is H of x1. H of x1 is fx. As soon as one point is determined, the entire function is determined, is one of the theorems that we proved last time, because any convex set is connected. Okay. So that was the first theorem that we proved last time, the uniqueness part. If you have a connected set, then any two lifts are the same, provided they agree at one point. So we are making it agree at one point, namely f of x not equal to r naught, g of x not equal to r naught. So this g is unique. So this is the consequence of whatever we have proved last time, right? Now this allows us to define a very popular concept, but it's not very well understood or handled just, everything obvious and so on without rigorously. So we can do it very rigorously as follows. Okay. Start with any function defined on an interval. Okay. Look at one single condition, that fa equal to fb. Okay. Even this condition can be forgotten for a while. Let it be there for a while. Okay. Fa equal to fb. By the above theorem, there is a map G from AB to R such that E of GA equal to FA, starting point, anything you want to take. Okay, I have not bothered about what should be G of A. E of GA is FA. There are lots of choices for GA. Indeed, once you choose one choice, any one single thing, so E GA equal to FA, anything got by adding an integer to this one, GA plus N. E of GA plus N is also equal to E of GA. So there are plenty of choices here. Doesn't matter. For each of them, you will get a G. Okay, unique. The moment you choose this one, there's a unique. Otherwise, there is a map such that E of J could have a. Okay. So this G is, E of Gx equal to Fx for all x. Okay. The uniqueness part of the theorem says GB minus GA does not depend on the choice of G. There are several functions like this, but GB minus GA does not depend upon the choice of G, because any choice differs by an integer n, and the entire thing is shifted by an n. So difference will be, you are adding n here, you are subtracting n here. So this is always a constant. Okay. So here I have still not used the fact that FA equal to FB. Okay. So far. But to want to define a winding number, then I have to use FA equal to FB. This winding number delta F is given by this difference GB minus GA. This itself is an integer, the number. Otherwise, it's just a real number. FA equal to FB. Okay. E of GB equal to E of GA, because both of them are equal to FA equal to FB. Okay. When two points are having the same image, E of some x equal to E of y minus x is an integer. So that is a property of E I have used again. So this is a number. Okay. So this number is called the winding number. I am denoting by delta or sometimes W. I think your book writes it as W. Okay. This number is now defined, completely defined without any ambiguity. It doesn't depend upon what G you choose. And we have chosen that this is possible. That is very important. We have proved that there is such a function. In fact, such a function is unique the moment you determine one point. Okay. So the path lifting property has been used very systematically. The second part, namely homotopy lifting, will tell you that if the starting point map F is homotopic to another map, say F1 and F2 are homotopic, then the entire homotopy can be lifted, right? Then this winding number will be the same for all of them. Okay. So that is the crux of the matter here. Okay. So any continuous function, so this is invariant of the path homotopy type of F. Okay, this is a consequence of the homotopy lifting property. All right. Now, suppose you have some function from S1 to S1 itself to begin with. Okay, then what to do? You can convert this one as in a standard way as a path by taking AB to be 0, 1 and then go to S1 by e power t, okay, and then follow it by F. So that's what you do. Suppose you have some function, then we shall consider the function F composite t from 0, 1 to E. First you take E itself here, okay, then follow it by F, and then you can look at, a lift of this one into R and apply the previous thing. You get delta of F composite T, which you can write it as delta of F. Okay. So e power t, remember et is e raised to 2 pi it by my convention, so cos 2 pi t, comma sin pi 2 pi t if you want to use the real notation. If you want to use a complex notation, it is I plus I times sin 2 pi t. So simple notation delta f we can use for all functions from S1 to S1. So this delta is called degree. That is why delta. Okay. So some people write it as a winding W, a winding number. Winding number is a very special kind of interpretation of this, the degree map. Having taken off topological aspects, now return to the geometry. Okay. Start with a unit speed simple closed curve of period L. So it is parameterized by the interval 0 to L. And what is S? S is some surface, not necessarily a surface patch. Any surface inside R3. Okay. Always our surfaces are inside R3. Start with a smooth family of orthonormal frames for S. What does this mean? A comma B span the tangent space. Norm of A equal to norm of B is equal to 1. A and B are orthogonal. And this N is A cross B. Okay. So this is orthonormal smooth family I have chosen. I mean, later I have just taken. I don't know whether it exists. Suppose there is such a thing, namely, starting with any S, I should have such a family all over S. Okay. Fine. Suppose now theta from 0 L to R is a smooth function such that the derivative of gamma is gamma dot. Gamma is a unit speed curve. So gamma dot will be a unit vector, right? Therefore, you can write it as cos theta times A plus sin theta times B. It will be a combination of A and B only because it is in the tangent space. And then what when the coefficients? Coefficients must have the property their sums of their squares is equal to 1. Okay. But we are writing it as cos theta plus sin theta. You can write like this, no problem. But the point is that this theta can be chosen as a smooth function. And up to a choice of the starting point, it will be unique. This is the content of whatever we have done so far. So that is not stated here in this lemma. Suppose there is such a thing. Okay, that is the part here. Okay, we can always do that is what we have done already. Okay, this part is not a supposition at all. There is such a choice. Okay, whatever. So suppose you have this one. The conclusion here is lemma is that the derivative of this theta with respect to t is nothing but the kappa g plus a dot the derivative of b. So this is the formula I have. This is now the geometric aspect of a unit speed curve on a surface. Before writing theta dot, I should know why this theta is differentiable, right? And that is justification comes from whatever we have done so far and it's today's and just an extension of that part just now. Okay, whatever we have done so far is necessary for this one, that there is such a theta. This is the part of the first part I am explaining it here again, namely, consider the smooth map F from 0L to S1 defined by Ft equal to gamma dot T dot with A. See, gamma dot is a smooth function. Okay, that's a vector. It's a 3 vector. You can dot with A. A is also a smooth function. Okay, you can write as AT actually, but we are ignoring such formalities here. Second coordinate is gamma dot T dot B. B is not a constant vector, it's BT. Okay, so that's another function. So this is automatically a smooth function. The point is that it takes values inside S1. Otherwise, it's a point, it is just a vector in R2. Why that is true? Because gamma dot is a unit vector. Okay, so gamma is a unit speed curve. Okay, now you apply the unit lifting theorem to this function, okay, to get a map G from 0L to R such that E composite G is F. Okay, all that you have to do is in the new notation put theta t equal to 2 pi gt, because in our formula E there is already 2 pi. So you multiply by 2 pi of G. Then what you get is precisely gamma dot is cos theta A plus sin theta B. It's just this part dot product is cos theta, this should be sin theta. Okay. So this is how we get this function, this statement here. Or you can write it as cos theta A plus sin theta B. Okay. So this is the justification for this supposition. Now let us work out theta dot. So this part is purely elementary computation. Totally elementary computation. Okay. So let us go through this. So gamma dot is cos theta A plus sin theta B. Okay. Remember that A and B are functions of t. So take the cross product with n, the normal vector. N cross n, remember n is perpendicular to both A and B. N itself is A cross B. Okay, so n cross gamma dot will be, when you product with A, it will be B. So it will be cos theta B here. And this one will be minus sin theta A, because n cross B is minus A. That's all. Okay, so this follows n cross gamma dot is minus sin theta A plus cos theta B. Now take the derivative of this one. Gamma double dot will be, by Leibniz rule, cos theta A dot plus, when you differentiate this part, sin theta B dot comes. Then I am going to take theta dot. Okay, no, cos theta I have to differentiate. So theta dot into minus sin theta A as it is, plus similarly theta dot into the derivative of sin theta is cos theta times B. Okay, so this is just elementary computation using Leibniz rule. Therefore, the geodesic curvature kg of gamma, which is by definition, this kg geodesic is what we want. We are going towards that one statement, right? So I am computing this term kg. Kg is nothing but n cross gamma dot gamma double dot. So this is a vector triple product of gamma dot and n. Okay, you have to take it in correct order. You can this cross dot also you can take. Okay, by associativity as a vector triple product. Okay, that's equal to minus. See, I am just taking, I have got these two things here, this one and this one. This and this, I am taking now the dot product of this. The dot product of this will be minus sin theta A plus cos theta B dot with all these things, which is, you can just see that minus sin square theta A dot B dot plus cos square theta B dot A dot, but this is, this is A dot B plus theta dot, these two cancel out, theta dot into sin square theta plus sin. Okay, so that is equal to theta dot, this is 1, minus A dot B dot. A dot B dot. Okay, so that computation will take care now, saying that if you bring that kg is this minus this, so bring it on this side, theta dot is this. Okay, now we can state Hoff's Umlauf-Sass. Umlauf-Sass turning angle theorem in English. You take a surface patch this time. Okay, this is for surface patch. R is some domain inside R2, maybe rectangle or maybe a disk, doesn't matter. So surface is inside R3. Take a surface patch where R denotes a closed rectangle. Now suppose gamma from 0L into the interior of R, sigma of interior of R. Don't worry about what is happening at the boundary of the rectangle. Don't take that part. Suppose the entire curve is parameterized simple closed curve of period L. This part is same thing as in the lemma, but only in the lemma this S was any surface. So here I am taking parameterized surface, namely surface patch. Let ABN be a smooth family of orthonormal frames along S. Okay, so that this always a convention. N I am taking it as A cross B, the unit normal at each point of surface S. Automatically it will imply that A comma B span the tangent space. Okay, this is always possible in the case of a surface patch. Okay, that we have seen. In the case of arbitrary surface, I have to make this as a hypothesis. Now here I am taking let. Okay, let theta from 0L to R be a smooth function such that gamma dot divided by norm gamma dot I have to divide by this one because I have not assumed that this is a unit speed curve. The parameterized simple closed curve. Okay, therefore I am dividing it by the norm. So now this is a unit vector. So by the previous arguments and previous lemma part of this lemma, you can write it as cos theta A plus sin theta B for a smooth function theta. Okay, so suppose you have written, so instead of suppose, now I am writing let. So this is theta has been chosen like this. Then all that you have to do is take the integral of theta dot from 0 to L, that is equal to plus minus 2 pi. The sign will depend upon whether you have chosen this theta going counterclockwise or clockwise. Okay, so sign will be somewhat fragile here. So if you change one of the A, sign of A, the sign of this one will be changing. That kind of convention is there. Up to that sign, it is always 2 pi. Okay, so this is the statement. What is theta dot? It's a variation, this speed, variation of theta. The sum total of variation is 0 to L, that is 2 pi. So just the curve just goes around exactly once, etc. There are several. I will come to the geometric interpretation of this one a little later. Okay, so let us see how to go towards the proof of this one. Okay, there are stages here. By simplifying the given data, okay, further and further. So 2 stages we will simplify it, so that finally I have replaced the surface by a plane. So everything is happening inside a plane. And then further one more step we have to do, and the final proof will be given next time. Today we will not complete the proof of this theorem. Okay, so that is the whole idea. So let us start. So first of all, I repeat, even before proving the statement, I am justifying why you can have cos theta sin theta. In fact, I have already done that in the previous lemma. Okay, that justification is the content of the last lecture. So again I have repeated it. T going to gamma t by norm gamma t is some continuous or smooth function taking values inside S1, the unit vector. Therefore, you can write it as some AT times A plus PT times B, where AT and BT are coefficients of this unit vector in the direction of A and B, right? So what is true is AT square plus BT square is 1. So you look at now this function f gamma depends upon gamma, AT comma BT. This is a function from 0 to L. Apply the theorem that we have proved last time. Lift it. There is a unique lift. If you choose one of the points starting with 0, suppose the image of 0 is something you want to choose, whatever, which will go to f gamma 0, where whatever that vector, then the whole lift is well defined and so on and so forth. Okay. Okay. After that, you have to just take lift as theta, twiddle, and put theta equal to 2 pi, multiply by the 2 pi of theta, so that it will just write cos theta instead of, otherwise 2 pi will come here hanging. So I have exhausted that theta and write theta as 2 pi of theta. Okay. Okay. So this W winding number I have used W of W is same thing as delta of FW. So I have to prove that this is equal to plus minus 1, which will mean that because there is a sign 2 pi multiplication, so this integral will be equal to plus minus 2 pi. Okay. Integral, remember, integral of a differentiated function by the fundamental theorem of integral calculus, nothing but theta b minus theta a. B and a are here L and 0. So it is theta L minus theta 0. And that is the winding number. Okay. Only thing is, this time you have to multiply by 2 pi, because this theta itself is 2 pi times theta twiddle. All right. So Hopf's theorem is equivalent to showing that the winding number, the degree of this map is plus minus 1. Delta of f gamma, or I can write it as W of f gamma, is winding number. Both the notations are used anyway. Okay. So what is it exactly, if you look at, this is a general thing. If you have two vectors inside R2, okay, one of them is a unit vector A, okay, then the dot product of this vector with that is nothing but cos theta. The angle is theta, then cos theta. This angle I am denoting by this hat here. This is the notation used in your book also. Gamma dot A just denotes the angle of gamma dot, which is some vector measured from A. It's another direction. Okay, the measuring is taking from A to gamma dot. So this is the notation. So that is theta by the very definition. So cos theta is equal to this dot product. Okay, therefore theta dot, just what is theta dot? It is the total, it is the rate of change of theta. Integral of theta dot is the total change. Okay, so that's why, so theta L minus theta 0 is integral of theta dot along this curve. Okay, so theorem asserts that if you start with a simple closed curve, no matter what it is, I mean, it need not be unit speed curve and so on. Simple closed curve inside a surface patch. Okay, the rate, the total change of angle as you keep going along is plus minus 2 pi. So it is just like if you are moving along the curve, keeping your eye always tangential to the curve. Okay. When you come back to the original point, you would have just made one rotation about yourself. It is like a top turning. When you top is turning, it will keep going around here and there, but it is turning very fast around itself, right? Like the earth is moving around itself a lot, right? So earth moves 365 times around itself by the time it makes one single round. Okay. Whereas for a simple closed curve, what happens is the person moving along the simple closed curve, keeping his eye always in the tangential direction, will be turning his entire himself exactly once, maybe in the clockwise direction or in the opposite direction. This is the meaning of Hopf's umlausas. By the way, you don't have to keep your eyes tangential. You can keep it normal also. Okay. Or you can hold a rod which is always perpendicular to the curve that you are moving along. Okay. You go around and come back, the rod would have just moved, exactly 2 pi times. So it would have first changed its direction once, the same direction again it will change once. Okay, so this is the interpretation of this one. The important thing here is that the curve is not a plane curve. It is on a surface patch is the important thing, not on an arbitrary surface. On an arbitrary surface, this theorem is not true. Okay, so let us see how we go about this. Once again, I have told all these things to you, but I will repeat it. It should be noted that unlike in the lemma, here we are assuming that the curve is unit speed parameterization. We are not assuming that curve is unit parameterization. That's not needed. So when you are moving along the curve, you are free to choose your speed, no problem. Okay. On the other hand, we are assuming that it is simple closed curve. So it is smooth everywhere and does not cross itself. That is very important. Okay, stronger hypothesis is that. We know that S is now a single surface patch. Therefore, the hypothesis that there is a orthonormal frame, that is assured. Okay. So indeed, we can start with sigma, which is the parameterization. Then you can just take sigma u, sigma v, normalize them, and then take sigma u cross sigma v divided by the norm. So this we know already. Or you can take sigma u cross sigma v, sigma u cross, and then orthonormalize. That is the best way to do the whole thing. Okay. So there are methods to it. Okay. So let us start reduction process for the proof of Hobbes' theorem. So first of all, for simplicity of writing down the proof and so on, we can assume that the domain R, okay, which is a subset of R2, contains the origin. And sigma of 0, 0 goes to the 0 of R3. Okay, the base points by shifting the origins or by choosing the coordinate itself, I can assume this way. Okay, if L denotes a linear span of sigma u at 0, so take the derivative of sigma u at 0 and sigma v at 0 and look at the span. That is a two-dimensional subspace. It may not be the xy coordinate space, right? It could be anything. But what does your linear algebra say? If you have two-dimensional subspace of a three-dimensional space, okay, look at the three projection maps: projection to the x-axis, projection to the y-axis, and projection to the z-axis. There are three projection maps, right? Two of them must be linearly independent. Okay, this is more generally if you have a k-dimensional space of Rn, okay, the k of them must be independent. Which k of them, I don't know. Okay, so you can take, say, x coordinate and y coordinate, or x coordinate and z coordinate, or y coordinate and z coordinate. So call them as x and y coordinates. Whichever two of them are independent, choose some, then call them as x coordinate and y coordinate. Solve by just renaming the coordinates. So what you have got is a projection map from R3 to R2 now. Okay, so xy is equal to xy. Okay, what I have assumed is that the linear span of sigma u and sigma v at the origin, okay, projects surjectively, surjectively onto R2. Okay, that this is surjective mapping. Okay, d pi composite sigma is nothing but d of pi, which is pi, this projection map. D of sigma naught is the derivative at that point, which will consist of the two vectors sigma u and sigma v. So this is the total derivative notation. Okay. So remember, in terms of this notation, we have set up the Jacobian matrix is surjective. That is the meaning of this one, right? From where to where? From R3 to R2. Once you take this pi, is R2 to sigma, it's R2 to R2. Therefore, it is an isomorphism, right? So it's invertible. Okay. So I can apply what I can apply. I can apply my inverse function theorem. In fact, I have proved this theorem already, that And in such a thing, in a small neighborhood of this origin, the entire function looks like, the entire surface looks like the graph of a function. This was a theorem that we proved. Okay, you can directly apply the inverse function theorem and this psi is a diffeomorphism, and then rewrite sigma composite psi, which will look like xy going to x comma y comma alpha xy. That it looks like a graph of a smooth function. So applying the inverse function theorem, okay, I can assume the surface coordinates are changed. Surface is not changed. Remember that, nothing else. Coordinates are changed so that in the new coordinates, some small patch of the surface will look like xy going to x comma y comma alpha xy, some smooth function. So this is my sigma now. Therefore, computation of the derivatives, etc., will become easier. This is now graph of function. Okay, so this is the picture here. In a small neighborhood of this, say this is V, the function, the surface looks like a graph. So elsewhere it might have gone, we don't know. So this is my sigma now. Okay, the whole thing is also defined on the whole of R. Okay, but there it may not be the graph of a function. Okay, inside a small neighborhood is graph of function. The curve itself, this is the curve omega. Image of this omega is gamma. See, when you have parameterized curve inside a parameterized neighborhood, namely in a surface patch, you can always write it as this gamma is part by taking sigma inverse. This is omega. In other words, gamma is omega composite sigma. Sigma operating upon omega. So I have a curve here. The image of this curve is that curve. Okay, so that is the general hypothesis. But this curve may not be inside this V. It may be somewhere. Okay, only on V, we have this formula xy going to x comma y alpha xy. Okay, so this is the first simplification. But now I want to do what? Next simplification. The idea is to shrink the curve gamma so that it will come inside the image of V, that is W. Sigma V is W. Okay, so let us write gamma equal to sigma composite omega, where omega itself is a parameterized simple closed curve inside R. Okay, so we want to shrink this R so that it comes inside V. Then image of this sigma under inside that will be coming inside W. So now we have to do it in the plane. In the plane, I want to shrink this omega. The point is that we will do it by shrinking means what now? Homotopy. Why we are allowed to do homotopy? Because we have proved that the winding number is independent of the homotopy class. The degree is independent of the homotopy class. That's why we can do that. Okay, that is the whole idea. So put gamma R of t as R ranges over 0 to 1. I don't want it to be 0. Okay, fix any, say, half to the 2, whatever, till you need it, till it comes to inside this region. See, I am pulling it back along these dotted lines. So what you have to do, I'm just rescaling sigma of R times omega t. So omega t is a number inside R2, right? So R times omega t makes sense. So if R is 0, it will be 0. Okay, for sufficiently small r, this entire omega t, because this is a bounded function, will be less than the norm of that one will be less than some delta. So you can bring it whole thing inside this V. Okay, so choose R. Okay, from 1 to whatever, say R naught. Okay, then you can assume that the final result here is such that this f of sigma r, f of gamma r, this gamma r itself is inside. Okay, the winding numbers haven't changed because it's a homotopy. Okay, so we can choose r sufficiently small, the gamma r lies inside W. So the conclusion of this step is that the entire curve is also inside the surface patch here, xy going to alpha of xy. Okay. Whatever you have done so far amounts to saying that without loss of generality, we can assume that the surface patch sigma itself looks like xy going to alpha of xy. Okay, everything is happening inside this. So if you prove for the curve here, we would have proved it for a general surface. That is what it is. So now we want to consider another homotopy. Okay. Remember, still the curve, the surface is not a plane surface. There is alpha. We want to get rid of this alpha also. Okay, we want to bring everything into the xy plane. That is what the next thing is. So that is a bit easier actually. What we are doing is, we are pulling it now in a vertical direction like this, everything like this. So once it is inside the graph of the sum function, you can put it. That means what? See, this is alpha, x comma y comma alpha xy. So I am putting r times alpha xy, pulling it down. When r equal to 0, it will lie, the z coordinate will be 0. So it will lie inside this plane itself, x comma y. Right? Whatever curve is there, it will be some curve. It is not a xt comma yt. That is the meaning of the curve. Okay. So let us do that. So this is what I am doing. xy going to x comma y comma r times alpha xy. Okay. So this time, again, we are not changing the curve. Okay. Curve will be coming along the surface, but we are considering a family of surfaces which comes slowly down to the surface patch, namely the a portion of the xy plane itself. So when r equal to 0, we have got this one. So this is again another homotopy. So curves will get homotoped. So again, the function what we get, all this f gamma t, they will be homotopic to each other. Therefore, the winding number hasn't changed. Okay, so this w of f gamma hasn't changed. Okay, now the new thing is what has happened? The surface has become plane. Okay, it's a plane curve. Now one more reduction is necessary. See, finally we have to got theta dot in terms of this a, b, and n, right? So that kg is there, etc. is there, right? So we have to compute that. So we have to use the orthogonal frame. The angle is measured with the orthogonal frame. The orthogonal frame was something which you had no control. That was something sigma. So in this process, it will give you some orthogonal frame. But the surface now is a plane surface, xy plane. So what is the normal? Normal is always the unit vector in the z direction. So one simplification is over. So the normal is a constant vector now. But A and B are non-constants, may not be constants. So they themselves, as point moves along the xy plane, the frame itself keep moving. The surprising fact is, if the frame is a constant, we understand what's going on. The surprising fact is that even when the frame is moving, the total angle measurement will be the same. It will be always plus minus 2 pi, whichever. So this is defying the common sense, because we are changing the measurements and so on. The glitch is either that the frame is completely defined on the entire of the disk or the entire of the domain. The domain is consists of either a disk or maybe a rectangle, doesn't matter. The frame never vanishes. Okay, they are non-zero vectors. They are actually unit vectors. If that is the catch. If that is the case, then you can always move it. You can always move it. There's no problem. So this is the whole idea here. Okay, the orthonormal frame itself, when it comes back along the curve, it will not change its direction. It will not have moved into 2 pi. It will have moved 0. See, you take A, that's a vector, right? Tangent vector, moving along the curve. When it comes back, would it have moved 2 pi angle? Would it move? No, it would have moved 0 angle. No, it will turn in some direction and again it will turn back also. This is the whole idea. Okay, therefore, our total angle will not differ. But you see, this explanation is not a proof. We have already proved it, but people don't understand the proof. That's why we have to explain, and the explanation is not a proof. Okay, many people just give explanations. Explanation is not a proof. Sometimes there is a proof which you don't understand why something works. So if people start giving such words and which are not exact, which are not proofs, okay, this is what happens, and people seem to like it. Okay, inexact explanations instead of exact proofs. Okay, so coming back to the case when I reduce it to the constant frame itself, so that there is absolutely no confusion. Okay, so reduction to the case when the reference frame is a constant. What we have got is that the normal vector is a constant, because now the surface is a plane. Okay, so only the first two are changing, so we don't have to worry about the 3-dimensional case. Now we have 2-dimensional case, and this will be now, because orthonormal frame, this will be change is taking place in SO2. Okay, 2 by 2 matrices which are invertible, which are orthogonal and determinant 1. Okay, no change of direction also here, no orientations are changing here. So function is taking values from SO2. Each vector, A comma B, if you write, that will form a matrix inside SO2. Okay, 2 by 2 matrix. So I am just writing A comma B here. Okay, that is a frame. So look at FP equal to AP, BP, where P range is over the surface patch. Keeping the surface and the curve unchanged. We are not going to change them, but we are going to change the frame now. We are now going to change the frame of reference. Okay, since we are only doing the changes in R2, the normal vector is never changed. Okay, that is also one of the things that you have to do. All right. So consider now another homotopy. Remember, every homotopy of any of the data influences or in turn gives you a homotopy of the final function f. Therefore, when you lift that f, okay, and define the winding number is not changed. So this is used several times here. That is why I have to separate it out and put it as a purely as a topological result, which we did last time. So what I'm going to do here is look at this function p comma r going to f of r times p, where r is from 0 to 1. Okay, where p is inside r. Okay. See, for all these points, for the whole of R, it is defined. So R times P will be also a point of R because R is a convex domain containing the origin. F of 0 is also a frame. It is not become 0. It is a it is a pair of unit vectors which are perpendicular to each other. Right? This F is defined on the whole of R2. That's why. So P comma R going to F of RP. So that's homotopy. So instead of measuring with the given when P equal to 1 FP, we are measuring with it RP. This is another function. Okay, so let us denote the corresponding angle F of FRT. See, FR I have to write because now depends upon this one. This is just FT or F gamma T. It's cos theta, this R will be there. Depends upon this R. Plus I sin theta R of T. Where gamma dot by gamma norm gamma dot is the same thing, but these ARPs and BRPs are changing. Therefore, cos theta, sin theta are also changing. That is homotopy. So F1 is F gamma, and F0 is another function. They are homotopic to each other. Therefore, the winding numbers are the same. But now F0 is a constant frame, right? For all P, F of 0 times P is F0. So P will keep moving, but F of 0P is the same. So we have converted the problem of measuring the angle with respect to a moving frame into a constant frame, with respect to a constant frame. Okay, I think I will stop here, and next time we will just prove this theorem for the the simplest case, namely a plane curve, and we are measuring the angle with respect to a constant direction. Okay, so the hypothesis is that now we have a plane curve which is a simple closed curve. Measure the tangent direction along any given direction. So you can choose your direction to be x-axis also. Okay, then this integral of theta dot is precisely equal to 2 pi or minus 2 pi, depending upon finally that part we have to still decide whether we have taken anti-clockwise, clockwise. Okay, we have not assumed the simple closed curve is parameterized anti-clockwise or clockwise. That part we will leave it. Okay, so this will be done next time. And one more word I can add. That was the only version which Hoff proved. He never bothered to prove this general statement. He said general statement will be obvious. That is the kind of mathematics they did in those days. Even for this simplest case now, the proof is not obvious. Many authors have given wrong proofs. Okay, so let us do this next time. Any questions?